The sign function for scalar variables can be defined for real values like this, 1 or -1, depending on if it's in the negative or positive. If z is a complex variable, you can generalize this formula in this way. And you should think of this formula as essentially the numerator involving the absolute value of z and then divided by z. And now we're going to generalize this to matrix functions. The starting point is, it's a kind of naive method. You just take this formula where, okay, we already know how to compute, well, the square is obvious, square root also, and division is just matrix inversion. So that gives us directly a naive method to compute this sign function. You can write it in like a programming language like this. So you square the matrix and then you take the matrix square root of the square, and then you multiply it with the inverse. You can do it from the left or from the right. So that's what we call the naive method. But so now we already learned how to compute the matrix square root. So it turns out that you can combine this naive method with the algorithm to compute the square root. So in particular, the Newton method for the square root. This is Newton's method for the square root, but note that we now want to apply it to a square. So wherever we have an a, we're now going to insert a square. It turns out that you can do even better by doing, so we're going to do a change of variables. We define the variable s, which is so a inverse times the x variable, which is what the iterate for Newton's method. And we want that xk approach this square root of a. Yeah, so if we change this variable, then we get that, so a inverse times the square root of the square of a. And we did this change of variables such that the sk, if it converges in the sense that xk converges, then it will converge to this. And that's in fact the formula we had for the matrix sign function. So this here will directly converge to the matrix sign function. So the xk up here would converge to c, but okay, since we're actually interested in the matrix sign function, we can use this iterate to go directly to the sign function. Okay, it turns out that you can now rephrase the algorithm, so this algorithm, using only sk, and that will simplify some things. The initial condition for x was that we should start it with a matrix, so we start with a squared, okay, but a inverse times a squared, that just becomes a. So the s iterate should be initialized as a. This is just the definition of the xk iterates. So what we had up here. So this was xk plus 1, so we just insert that here. And now we will see that this can be simplified even further. Our goal is to obtain something like sk, and in fact here we already have sk. We want to obtain something like sk here as well. So we move in the inversion. So that means we have to change the order of a and x. But in fact, since a and x, or a inverse and x, they commute, we can change the order here, and this is sk. So we are now obtain this is a formula only involving sk and not involving x. So we have here, we initialize S with a matrix A, and then we compute, we take the sum of the S and its inverse, and then we take 1/2, and that's our new SK. And because XK converges, this will also converge. So, and it's going to converge directly to the matrix square root.